All right, we continue our discussion of force and motion and pick up with our discussion on friction. If you remember, at the end of our last lecture, we had introduced this idea of friction, and we talked about how these rules for friction are just that. They're rules that are typical of how friction behaves and not laws. And in addition, these relationships that we see in friction are not vector relationships. There are no vector symbols over the forces because the direction of the friction force and the direction of the normal force are in different directions. But the magnitude relationship here is typically a good relationship. So again, there are two types of friction. There's static friction, which is friction where there's gripping and there's no sliding between the surfaces. And then there's kinetic friction, where one surface is sliding past the other in some way. Generally speaking, kinetic friction is the friction which occurs when the two surfaces slide or scrape by each other, and it has roughly the same value regardless of how fast the surfaces are sliding or how big they are and so forth. So that relationship F friction, small f friction, equals mu times normal force, that's pretty much what we use as our relationship for kinetic friction. Okay, now we usually use a subscript K on our value for mu and our symbol for friction, the small f, to indicate that we're talking about kinetic friction here. So F sub K, the amount of kinetic friction force we get in newtons, is equal to the coefficient of kinetic friction, right, times the normal force, okay, which is our F sub n. So again, both the friction force and a normal force are newtons. Mu sub k is a unitless quantity, and again, mu sub k is important to use mu sub k, and we're going to see that we're going to distinguish between that and mu sub s, which is our coefficient of static friction, because these aren't necessarily the same size units or same size variables. Now, static friction is the force of friction that keeps one surface from sliding by another surface when a force is applied. So this is kind of the gripping force. So if you tipped your desk or your table up a little bit and your physics book didn't slide off your desk, the reason it's not moving and sliding off the desk is because of static friction, gripping the book between the book and the desk. Okay, so static friction is you want to think of it as kind of being the smart friction. It will adjust itself to whatever value it needs to be to keep the object from accelerating. So in other words, if your desk were perfectly level and your physics book was sitting on it, then obviously the amount of friction force we need to keep the book sitting there is very, very, very small. Ideally, it would be zero, but so the static friction force could be very, very small or zero in that case. But as we tip the table upward, right, tip your desk upward, the book doesn't move. So the amount of static friction is increasing as we tilt it higher and higher and higher until eventually the book does let loose and slides down the table and lands on the floor probably. Okay, so when it lets loose and does start sliding, that's where we've gotten to the maximum static frictional force. So again, static friction can vary. Okay, the value for the static friction can be anywhere from 0 up to its maximum value. And the maximum value, F sub s max, the maximum static friction we can get, is mu sub s times the normal force. Okay, so mu sub s is our coefficient of static friction. And typically speaking, generally speaking, okay, mu sub s is a little bit bigger than mu sub k for most materials. Again, every material interface, whether it's wood on wood or wood on metal or metal on glass and so on and so forth, those coefficients of friction are just general numbers that describe the proportional amount of gripping you get for an amount of normal force for those different surfaces. And that is different not only for surfaces, but even for the same two surfaces, like rubber on concrete, you're liable to have a value for mu sub s for rubber on concrete that's generally speaking, mu sub s will be bigger than or roughly in the range of mu sub k. But it's not uncommon for that mu sub s value to actually be larger. So we have to be careful. Mu sub s is used with static friction, mu sub k is used with kinetic friction. So we can, if we imagine taking our physics book and setting it on a flat table here, flat surface, obviously the free body diagram would look something like this. We'd have the weight of the book pulling down to the center of the Earth. That's the force of gravity from the Earth. We have the normal force of course, which is balancing, in the case of the book sitting on a level surface. That normal force is kind of balancing the weight force in this case. So F sub n equals mg in the case shown here. And then if I apply a force, let's suppose I try to just push the book a little bit, put my finger on the edge of the book and try to push it to the right a little bit like that. That's my applied force. And I'm going to get some friction force opposing me. Okay? And until the book starts to slide, I'm dealing with static situation. Again, remember that word static, always think of the word rest, right? Things aren't moving. Think of the words rest or not moving when you hear that word static. So in this particular case, as I push to the right, there would be a net force to the right unless the static friction is exactly the same size I'm pushing with. And so that's the interesting thing here. As I start to push this book to the right, looking at this graph down here, what we have happening is, as I push a little harder, my static friction gets a little harder. If I push even harder, the static friction gets harder, right? And so what happens is it stays proportional to me. The static friction adjusts to however hard I'm pushing, right? Until I get to this peak value, F sub s max, right? So when we get to F sub s max up in here, let me see if I can write that down there, F sub s max, right up at the top there. When I get to that maximum value up here, if I push harder than that, then what's going to happen is now the friction actually drops off a little, because now the object starts to move. Okay, so the object starts to slide, and once we're sliding, we're into kinetic friction, and kinetic friction has a steady value just based on the on the value of mu sub k. Okay, so that would be a typical curve. So that would be the kind of thing we'd see happening if we graphed the amount of friction force versus the applied force. As I push harder and harder to the right, as I increase the force this way, my friction force will go up, holding steady with me, balancing me, keeping the object from moving. And once I overcome it, the book lets loose and starts to slide, and then I have a nice steady amount of friction, which is typically a little bit less than the peak amount there. So again, as I've mentioned, mu sub s, the static coefficient of friction, is usually larger than mu sub k, the coefficient of kinetic friction. However, these coefficients do depend on the materials which are in contact and their physical conditions. Obviously, even surfaces that get wet, if it's humid, the surfaces may behave differently. Obviously, if somebody lubricates the surfaces, our mu values will change quite dramatically. So these mu values are really just ballpark numbers. Our textbook lists mu sub s is about 1.20 and mu sub k is about 0.85 for rubber on dry concrete. Okay, so if you were driving your car on a concrete road, obviously then the amount of friction that you get is going to depend on whether your tires are skidding, right, sliding, laying down rubber on the road, or whether they're gripping the road. So you actually have more gripping force than you do having sliding friction. You have more gripping friction than sliding friction available. What that means is that you can stop your car the quickest by applying the brakes in such a way that you almost skid on the road, but you don't. In other words, we want to be right up at the tip, right up here at the tip of this curve, right? That's where we're going to get our maximum amount of friction to slow our car down and stop it. So if I want to stop my car as quickly as possible, in the old days without anti-lock brakes, you would slam on your brakes and you would skid. And you'd get this much friction, which isn't bad. You get quite a bit of friction by slamming on the brakes and skidding. But unfortunately, when you skid, you start to lose control of the car. When you're skidding on the road, when your wheels are not gripping and they're sliding on the road, right, you turn the wheel and so forth, and it really, you don't have control over the car anymore. So if you've ever hit like some really slippery ice or snow, you know that you can lose control of the car. So the downside of the slamming on the brakes and skidding effect is that not only are we not getting as much friction as we could to slow the car down, but we lose control of the car in many cases. Okay, so with the idea of anti-lock brakes, we want to try to put the brakes on. If you were driving an old-fashioned car without anti-lock brakes, say a Classic or something, and you wanted to stop as quickly as possible, you're driving down the road and maybe a child runs out in the road in front of you and you want to stop and avoid hitting the child, so you want to stop as quickly as possible. Ideally, what you'd want to do is push on your brake pedal in your car hard enough that you're almost skidding, but you're just not skidding. right at that little touchy point. And usually in a panic situation, well, even not in a panic situation, it would be very hard for people to judge exactly where that point is and to hold the brake pedal down with exactly that amount of force, right? In other words, in a panic situation, usually your reaction is just slam on the brakes, okay? And certainly no one's going to is going to be talented enough to be right up at this point, right on that boundary between gripping and skidding. But that's where we want to be for maximum static. So what this invention of anti-lock brakes did was they created a sensor. They hooked a sensor basically into the wheel to indicate whether the wheel is turning or not, right? And it's a feedback system into the braking system. So when you slam the brakes on in an emergency situation, or you just put the brakes on and you're don't know how hard to push on them, and you push on them just as hard as you can, what'll happen is if the wheel stops turning, that is if the wheel starts to skid on the road, that means you're over in here, and what the sensor will do is feedback and tell the car's braking system to reduce the braking force. All right, and then once the wheel starts to roll again, it will kind of tell it, okay, now increase the braking force. So what's going to happen is, ideally, if your anti-lock brakes are adjusted right, you kind of teeter-totter, you go back and forth right over the top of this peak here, and of course that's actually what you feel like when you feel the thumping, if you will, that little rhythmic thumping that happens if you've ever had your anti-lock brakes kick in. That's what's happening. It's kind of going, it's almost like pumping the brakes. They used to tell you to pump the brakes, right? That was the old-fashioned way of trying to do exactly this, is if you hit the brake hard and then release hard and release, that you're hopefully going over top of this thing like this, right? But of course, pumping the brakes, you could have quite dramatic and not as big an effect. If you had a computer controlling it, you could stay right up near this peak right up here and get some extra friction. And so anti-lock brakes have been a great invention, and I think they're pretty much standard on any car today. They might even be legally required. Again, if they're not working properly, could be a problem. But if they're adjusted properly, wonderful invention. And the other advantage is not only that you're getting more friction to stop faster, but you don't lose control of your car. You remain in control of your vehicle. So that's another very, very big important selling point of anti-lock brakes. You remain in control of your vehicle. Okay, because when your wheels are still gripping the road, if you're up at teeter-tottering on that, you're still gripping the road. Your steering wheel is going to still be allowing yourself to maneuver around the potential hazard as well. All right, let's see how well you're understanding this so far. Here we have a diagram, a picture of a cement truck, concrete truck rolling along. The brakes are slammed on that speeding cement truck, and it comes screeching to a halt. Okay, so we're going to pretend that it doesn't have anti-lock brakes just to keep our thinking simple here. All right, so let's say the truck's flying along and then it slams on the brakes and it skids sliding on the road and it stops over here. So it skids to a halt with its wheels sliding on the road. The question is, if the truck were heavily loaded so that it was twice as heavy, let's suppose it was empty the first time, so it slides to a stop here when it was empty, right? It was just the cement truck. Now it's filled with concrete, right? We've got all kind of concrete in here, and the truck is twice as heavy. What's going to happen to the skidding distance here? Okay, what's going to happen to the skidding distance? So, think about that. Avoid the temptation of trying to just guess or use your everyday thinking, because again, as we know, sometimes that's, you're probably going to be about 50-50 on that. Some things your brain has got figured out properly, other things your brain has made up rules that aren't quite right. Okay? And so try to use the rules that we've been learning here. So you may want to pause the video at this point, think about this problem, maybe draw some sketches, reason through what you're learning here about F equals ma and friction forces, and see what you think the answer is. Okay, I'm not sure what you thought the answer was, but the answer is that the stopping distance remains the same. Okay, and if that's surprising, let's kind of work through this and think about this. So I'm just going to very simply, I'll just draw it as a car here. So there's our vehicle initially, and let's suppose it has mass m and it's moving along and it's going to skid to a halt, right? So what's going to cause it to skid to a halt? It's going to be the stopping distance here is going to depend on the initial speed and the acceleration. All right, so that stopping distance we'll say is some amount, well, I'll just call it d. How about d for distance, okay? And that stopping distance, of course, is going to depend on the amount of friction, obviously, and we'd think that the mass of the vehicle may enter into it as well. So how much friction do we have in case number 1 here, where we have a mass of m? Well, if we think about it, we draw our little free body diagram here. We have the car. It has a weight mg, right, or else the cement truck, weight mg. It's got a normal force. If it's on level road here and nothing else is pushing down on it, then the normal force is going to balance the weight force, right? So the force that's actually going to stop the truck, all right, is the friction. And here we said, let's just assume it's kinetic friction, that the tires are sliding. So what is the friction force? The amount of friction force we get is mu sub k times the normal force. So in this particular case, the amount of friction we get here is mu sub k times m times g, right? Because the normal force is equal to the weight of the vehicle. And so when we use Newton's second law here and we say, well, let's add up our forces in the x direction. We know there's no acceleration up and down here, right? The car is decelerating along the x direction. So the amount of force we have here, if we just get into the magnitudes, we have amount of force of mu sub k mg to stop the vehicle. And that's equal to the mass of the vehicle times the acceleration of the vehicle. And notice what happens here. The mass cancels. The acceleration, the deceleration of the vehicle is going to have a magnitude of mu sub k times g, which does not depend at all on the mass of the vehicle. Now, the other way to think about this, if you want to look at it, a different way, if you're sitting there looking at that going, well, geez, that's where the math seems to work out, but that doesn't seem right. Well, look at it this way. If I make the cement truck twice as heavy, then this is going to be twice as big, and the normal force is going to be twice as big, which means what? The friction force over here, friction is going to be mu sub k times the weight, which is 2 mg. So the friction force is going to double. The friction force is going to go to twice as big as it was before. So now you're thinking, well, wait, if the friction doubled, then why does the stopping distance or the deceleration remain the same? And the reason why is because an object that has twice as much mass also has twice as much inertia or sluggishness. So if we have twice the force acting on twice the mass, guess what? We get the same acceleration. Acceleration is still going to be F over m, or mu sub k mg over m. And once again, we see that the deceleration of the vehicle does not depend on the mass. And if we think about everyday life, that actually makes sense, because we know that the speed limit and so forth is not different for different vehicles. If you're driving a 75 Cadillac versus a 2015 Geo or Hyundai or something, little box car, little lightweight vehicle, or a motorcycle for all that matters, or versus a big pickup truck, whatever. Just think about the different vehicles on the road. They all have the same speed limit. Okay, they all have the same speed limit, because the bigger thing that affects the stopping distance more than anything is the coefficient of friction. The thing that affects your stopping distance more than anything, as far as the conditions of the car, is the tires. Okay, it's the gripping coefficient between the tires and the road. If you have better tires, you're going to have a better deceleration rate and a better stopping rate. Also, obviously having the anti-lock brakes, as we discussed, makes a big difference. But the mass of the vehicle doesn't really make a difference, because if we double the weight of the vehicle, we double the friction, but we need twice the friction to stop something that's twice as massive in the same distance. So the stopping distance actually stays the same. Now, sometimes students will say, well, wait a minute, don't trucks usually have different speed limits on the highway sometimes? And yeah, that's true. Sometimes, especially going through mountainous regions or regions where the road turns and curves a bit and so forth, a lot of times they do limit the speeds of the tractor trailer trucks and so forth going through the mountains. That's more because of the amount of energy those objects carry, and if they do lose their brakes or they do wipe out, they can do a large amount of damage compared to a regular vehicle, right? Those tractor trailer trucks are carrying a lot of weight, and so if they are going through the mountains and they tip over, or they lose their brakes and roll down a hill, the energy that truck has is kind of catastrophic. I mean, it can wipe out a lot of property, do a lot of damage versus lighter vehicles. And so it does make sense in the mountains and in areas where the road's windy and so forth, that they may limit the speed of trucks, tractor trailer trucks, somewhat. But generally speaking, I mean, it's you know, a truck that's fully loaded should be able to be stopped in the same distance as one that's not loaded. Okay. Now you'll feel that if you've ever driven like a big moving van or a truck that's heavily loaded. Maybe you've got a load of gravel or mulch or something in your pickup truck. You'll feel that extra mass. I mean, you'll have to push on the brake pedal harder. Right? You'll have more friction force available, and so you'll have to hit the, you know, push on your brake pedal in your vehicle harder when you have all that extra weight and mass in the vehicle. So you'll sense that extra weight. But the point is, if you put your foot down on the brake hard enough, you'll have extra friction with the extra weight, and that extra friction will be just enough to balance the extra mass you have, the extra inertia of your mass, and you'll get about the same deceleration and the same stopping distance. And so again, just everyday life says that's the case, right? Because if a person's riding a motorcycle, they have the same speed limit as a pickup truck, right? A heavy pickup truck or something. And so that's why, because the pickup truck and the motorcycle should be able to stop in about the same distance. And it's going to depend mostly upon, again, that mu value. Okay, so now we've pretty much covered all these different types of forces. We've talked about you know, the gravitational force, the weight near the surface of the Earth is mg. We've talked about the normal force, which is that contact force. Anytime two objects are in contact, there's a normal force perpendicular to the interface or the surface where the objects are touching, and it goes up through the object of interest perpendicularly. And then we've talked about the air resistance force, how as something goes faster and faster, the air resistance force gets bigger and bigger, and obviously larger objects will be grabbing more air as well. We talked about the idea of terminal velocity, and then we got into talking about friction between solids, where we have static friction if the surfaces are gripping, and we have kinetic friction if they're sliding with respect to each other. Okay, so when you drive your car down the road and your tires aren't squealing, in other words, you pull out from a traffic light, your car is moving, but it's actually static friction if you think about it. Your wheels are gripping the road. So it's actually static friction. If you're driving carefully and not sliding on the road in any way, then it's static friction. It's doing the accelerating and the decelerating of your car, right? It's that gripping force, okay? Anyway, so now we want to get into more, we're going to get into some little more challenging mathematics here for the rest of today, and start to look at some ramp questions and some more challenging types of questions that are we're going to use the mathematics for. So here we have an example. It says, suppose we have a 2-kilogram block and we set it on a 30-degree inclined ramp. The coefficient of kinetic friction for the block on the ramp is 0.25, and the block starts from rest 3 meters up the ramp. How fast will the block be moving when it gets to the bottom of the ramp? And so, of course, the first thing we want to do is, of course, draw our picture, draw our little sketch of this. And I happen to choose to have the block sliding down the ramp to the left. Okay? You may have set up your picture exactly opposite. You may have set up a ramp going this way and put a block here, and that's okay. Right? That's part of what we get to choose when we do these kind of problems. So just to show you that it doesn't matter, I kind of purposely set this up with the block sliding to the left as it goes down the ramp. Okay? So we've got our 3 meters up the ramp, 3 meters height up the ramp where the block is currently. We've got our 30-degree inclination off the horizontal. We've got our mu value listed here, mu sub k, 0.25, which they told us, and they told us the mass of the block is 2 kilograms. So we're off to a good start. We've got our diagram, initial sketch of what they described to us here, and the next step, of course, is we need to get our forces labeled in, get our free body diagram drawn. Okay, so we have our diagram here. Next, we want to choose some coordinates, coordinate system. And as I mentioned numerous times, if there is an object moving in the problem, or an object that would otherwise be moving, we usually choose one of the motional axes, the motional direction along one of the axes in our coordinate system. So with a ramp question like this, typically we choose the x-axis along the direction of the ramp and the y-axis perpendicular to the surface of the ramp. Then I start labeling my forces in. They didn't tell me I was on planet Earth, but the assumption is I'm on planet Earth, and that's what's really the thing that's going to cause the block to slide down the hill here. And so I label that in my vector W or F sub G, as your book likes to use, for the force of gravity or the weight acting on the object. And again, as we talked about in a previous lecture, you either have to just memorize the fact that the inclination of the ramp here is the same as the angle between the weight vector and the y-axis, or you have to do some drawing of right triangles here and solve out and figure out what angles are what, okay? But it is possible to prove to yourself that this angle is the same as this angle, and so I've just gone ahead and labeled that in as 30 degrees. Now we draw what other forces are acting on the block. There's F sub n. The normal force is acting upward, okay, from the surface. Again, we put our pencil on the surface between the two objects where they're touching, and we draw a line perpendicular to the surface up through the object, right? So that's perpendicular there up through the object of interest, which in this case is our block, and that's our normal force, and we label that. And then the only other force acting in this problem is the friction, right? The friction is going to be acting opposing the motion, and so if the block's going to slide down the ramp, then obviously the friction is going to oppose that and act up the ramp, and so I drew my friction force in as up the ramp here in the positive x direction, and of course it's kinetic friction in this case, so we labeled in F sub k. And now we're ready to draw our free body diagram. Rather than tilting our heads the whole time, which is a possibility if you're in a big hurry, we tend to be disciplined here, and we draw our free body diagram, simplifying the diagram, getting rid of all the extra things in there we don't need. And so we take our XY coordinate system, we represent the object of interest. That block would be put as just kind of a bold dot in the middle of our coordinate system. And now we draw all the forces acting on it, and so we draw them all so they're acting away from the center, right, away from the origin. And so pushing forces are always drawn as like a pulling force, if you will. And here we have F sub n, F sub k, and W labeled into our diagram with angles. And so now it becomes a matter of starting to think about what are the size of these forces and how can I write them in component form. Okay, so the next thing we might do is we might say, well, I don't know how big F sub n is, right? It's not equal to the weight of the block in this case because we're on a ramp, right? So the amount of normal force, if you think about it, as the ramp gets steeper and steeper, the normal force gets smaller and smaller. The normal force is going to be maximum when the ramp is down at 0 degree inclination, when it's sitting level there. So in this particular case, we don't yet know how big the normal force is, but we can see from our diagram that F sub n here is in the positive y direction. So whatever that value is, I can now write the vector and say, well, my vector F sub n is 0i plus some amount F sub n in the j direction. Okay. Vector F sub k, similarly, we know F sub k just from studying just today. We learned that F sub k is mu sub k, the coefficient of kinetic friction, times the normal force. So even though I don't know, again, the normal force yet, I can write in that detail for mu sub k. I know that's how big the vector is. And now that's all pointing in the positive I direction, right? No j component. So now I can write vector F sub k, and I'd say, well, it's some amount mu sub k times F sub n in the I direction plus 0j. And so we've got our two of the three vectors already written. Now the weight vector, of course, we need to get that written in component form. And again, if we want to use this angle between the vector and the y-axis, we can do that. We just flip-flop our sine cosine rules. So in this particular case, our weight of our object, they had told us it was a 2 kilogram object. Let's just assume G is 10 here to keep our math nice and simple on this particular example. So if we estimate G is 10 meters per second squared, a 2 kilogram object would have a 20 Newton weight on the surface of the Earth. And so now we know the size of W, and if we flip-flop our sine cosine rules, we know the size of the x component for W is 20 times sine of 30 degrees, and that of course gives me 10, since sine of 30 degrees is 1/2. And then we take 20 times cosine of 30 degrees, and we get 17.3 newtons for the size of the y component. Now we just have to get our signs right. By looking in the diagram, we see that vector W here is to the left and down, so it's in both the negative I and the negative j direction. And so we put in our minus signs, and we can now write vector W as being minus 10I minus 17.3j. So now we have all three vectors, forces in the problem, and now we can start to apply Newton's laws of motion. Okay, so we're just going to transfer this over to the next page. We've got our diagram, we've got our three forces in component form. Next, we want to start to apply the laws of motion. And usually, again, the main equation, the main guiding equation in this of course, is we have our net force equal to our mass times our acceleration. It's Newton's second law, right? We're dealing with forces here. We'd like to try to get the acceleration of this block down the ramp so we can solve for its speed at the bottom. And so we're using F equals ma, but again, we typically do that along one dimension at a time. So looking in the y direction, that's the easiest direction to look in to start with, because in the y direction, this block, as it slides down the ramp, it's not going up or down at all, right? In our y direction, it's just sliding along, it's staying at the same height. So in the y direction, there is no acceleration, which means if we add up our y components of our forces, we should get the mass times the acceleration in the y direction, and this should be 0. So now we go ahead and add up our y components. Again, we look up here and we say, oh, well, we've got F sub n, we've got 0, and we've got negative 17.3, and those better add up to 0, because I cannot have any acceleration up or down. The block is not dropping through a hole in the ramp, and it's not lifting up off the ramp, propelling it, or, projecting itself up out of off the ramp in some way, like a rocket. So that acceleration has to come to 0. Therefore, those forces sum to 0, and that tells us the normal force is 17.3 newtons. That's a big step. We now have an additional piece of information using the laws of physics. Okay, we continue looking in the x direction, and we know that if we add up the forces in the x direction, we should get the mass of the block times its acceleration in the x direction. So looking in the x direction, what do we have here? We've got 0, mu sub k F sub n in the positive direction, and minus 10 units in the negative direction. Adding all those up, that will give me my net force in the x direction. That should equal the mass of the object, or the mass of my system here, which is my block. All right, and so the mass of my system is 2 kilograms times the acceleration in the x direction. And looky here, now that we know that mu sub k is 0.25, because they told us that, and we know that F sub n is 17.3, we can actually figure out those values, plug those in, along with the 10 here. That's another number we know. We've got our 2 kilograms times A. So the only thing we don't know in this equation now is A. And so we can take this equation, looking at Newton's law, second law of motion in the x direction, and we can solve it out for the acceleration. And what do we find? We find the acceleration for this block is going to be negative 2.84 meters per second squared. It's going to accelerate in the negative direction here, down the ramp, which is what we expected, and it's going to accelerate at a rate of 2.84 meters per second squared. Now that we know the acceleration of the block down the ramp, we can go back to kind of the beginning here and say, okay, now we know all the information, and we know we have a block here starting from rest of 3 meters up the ramp, and it's going to accelerate at that rate, what was it, 2.84 meters per second squared down the ramp. And so we should be able to figure out how fast it's moving after 3 meters. So this becomes a one-dimensional kinematics problem now. All right, we solved the dynamics part of the problem with free body diagrams and Newton's laws to get the acceleration. And now we just kind of start over and we say, well, the block's starting at position x0 equals 0. Might as well have it start at the center of the coordinate system, right? It ends up at x final equals minus 3. Obviously, in the y direction, nothing's happening. So this is just, like I said, just one-dimensional along the x-axis here. V original x is released from rest. V final x, that's what we want. That's what we're looking for. And we know the acceleration is 2.84 meters per second squared down the ramp, or in the negative direction. So now I go ahead and look at my equations, and I want to solve for V final x. And of course, this equation shown here is the one that kind of stands out. Excuse me, V final x squared equals V original x squared plus 2 times acceleration times x final minus x original. Again, signs are important here, right? So we get V final x squared equals V original x, which is 0 squared, plus 2 times the acceleration. Now again, the acceleration has to go in as a negative. If I miss that sign, I messed up. X final, it's 3 meters to the left, or in the negative direction from where it started. So negative 3 minus 0 gives me minus 3. We solve all this out. We get V final x squared equals 17.04. Okay? Now, when we take the square root of 17.04 on our calculator, it's liable to just tell us 4.13. Okay? Because remember, when we take an even root, we have 2 possible answers. The answer can either be positive or negative. So in this particular case, if we think about it, our velocity here, right, if that's what V final x stands for, is velocity, the right sign for that would actually be the negative root. So the final velocity would be minus 4.13 meters per second. Okay, it's going to be moving at 4.13 meters per second to the left as it gets to the bottom of the ramp. Now the question, if I remember, asked about speed. And so if it asked about how fast in terms of a speed, then I would answer 4.13 meters per second at the bottom of the ramp. And again, sometimes the reason they may ask for speed instead of velocity is, once again, they do not know how you set up your problem. If you'd have set up your problem like this with the block coming down the ramp that way, you would have got a positive velocity. So rather than them asking for a sign of velocity, they sometimes will just ask you what's the speed, and that way everybody, regardless of which direction you set this problem up, should get the same final answer of 4.13 meters per second. And again, because it's a speed, it's always going to be a positive. Right? Because the magnitude of the velocity, that is how fast something is going, is always a positive value. You can't have a negative length vector, right? Vector magnitudes are always positive. Okay, so let's look at another example here. This is one from your book. And it says, if a car's wheels are locked, kept from rolling during emergency braking, the car slides on the road. Okay, at least back in the day when I was growing up, back in the 70s and 80s, early 80s, when you slammed the brakes on a car, it would skid, okay? And that's kind of what they're referring to here. So ripped off bits of tire and small melted sections of road would form the skid marks. And that's evidence of the cold welding that happened between the tires and the road surface while the tires were sliding on the road. The record for the longest skid marks on a public road was reportedly set in 1960 by a Jaguar on the M1 highway in England. The marks were 290 meters long. So again, 100 yards, those of you familiar with 100 yards for American football, 100 yards is a little less, it's less than 100 meters. So 290 meters is over 3 football fields long. So that's quite a length of a skid mark to leave on a highway. And again, I don't know whether this is still the record, but this is the problem in your book. So it says, assuming that mu sub k is 0.6 and that the car's acceleration was constant during the braking, how fast was the car going when the wheels became locked? So again, our assumption here is that the braking is on like a level road. They slam on the brakes, they're skidding, so we've got kinetic friction happening, a nice steady amount of friction force acting against the car, slowing the car down. This is an example of, for those of you that are interested in forensics, I know a lot of times, we think about, biology, looking for DNA, and maybe if there was an explosion or gunshot residue, looking at the chemistry of that, and so on and so forth in crime scene investigation. But many times physics comes into play there as well. Okay, physics can be used to, you can look at the final positioning of things and look at evidence like skid marks and so forth, then you can backwards calculate to figure out what the original situation was. So here, we come along the road, we see an accident, perhaps the driver is not even alive anymore and no one saw it happen. We can use the physics, and from the length of the skid mark and some measurements of knowing some information about the tires and the road surface, such as the coefficient of kinetic friction, the length of the tire marks and so forth. Now we can use our physics to figure out how fast was that car going. What was the minimum speed that car was going when it slammed the brakes on? So again, the physics can be used as an important forensics investigation tool as well, and it's actually very important in the FBI for especially explosions, collisions, crashes, things like that. There's a lot of physics that goes into that, and we'll talk more about that as the semester goes along. But here we see a diagram. We see a picture of this car moving along at some original speed v0. It slams on the brakes, it's going to decelerate. It takes 290 meters here, is the assumption that it takes 290 meters to come to a stop, and mu sub k, is 0.6. Now I've just copied that information over a little smaller at the top of the slide for us to be able to refer to. And now we start to think about the free body diagram for the car. So again, obviously the motion's along the left and right direction, so we might as well choose our coordinate system x along that direction. Y is perpendicular to that then, perpendicular to the road surface. So there's the car as a bold dot in the middle of our coordinate system, and what forces are acting on the car? Well, again, we have the force of gravity, the weight of the vehicle, right? I like to use a W for that usually. And then we have the normal force pointing upward. That's the force of the road surface pushing upward on the car. And then we have the friction force to the left here. And the reason we have it pointing to the left is because in our diagram we assumed the car was moving to the right when it slammed on the brakes. So obviously if you had your car moving to the left, your friction force would act to the right. Obviously it's going to oppose the motion, okay, oppose the motion of the car. Now, there's our free body diagram. Now we start to think about what the laws are going to tell us about this situation. Obviously, in the up and down direction, nothing too interesting is happening, right? There's no acceleration up off the road surface or down into a hole or something like that in the road surface. So F sub n and F sub g are going to balance here, okay? And assuming that the constant acceleration is due only to the kinetic friction force, if we kind of ignore the air resistance forces as part of the stopping force, then the force is going to be directed opposite the car's motion, and we know that the size of the friction force, F sub k, is going to be equal to mu times the normal force, but we also know that if that's the only force acting on it, that's the force that is going to cause the car to decelerate. In other words, net force equals mass times acceleration. So in this particular case, the only force acting in the x direction is F sub k, and it's in that direction, and then that's equal to the mass times the acceleration of the car. So again, this comes straight from Newton's second law here, and we write that equation down because we know that thing must be true right there. Okay, so that's one piece of information. We know that that's kind of our guiding equation as to what must be true. Now we go ahead and say, well, the car's mass is going to determine the weight of the vehicle, and we know the friction force is mu sub k times F sub n, and therefore, since F sub n is equal to mg, right, the weight of the car is equal to mg, and the normal force is equal to that, since the forces must balance in the y direction. There's no acceleration in the y direction, right? So the forces along the vertical direction must balance. So F sub n is equal to mg. We can now take that up and stick it in here, right? You see where we're going with this? We can write then F sub k will have a size equal to mu sub k mg, and now we just have to plug that value in up here for F sub k, and now we're on our way to solving for the deceleration of the car. Okay, so if we take these equations and start to put them together here, we can see what's happening, okay? The friction force that's going to slow the vehicle down that was skidding is mu sub k times F sub n, at least the magnitude of it, right? That's our friction equation right there, right? This is what we talked about. That's the equation for static or kinetic friction. And the normal force here was mg, so the size of the kinetic friction force is mu sub k times mg. We know the acceleration is going to be equal to the net force divided by the mass. The net force here is in the negative direction to the left as far as our diagram went. And then we take negative mu sub k mg for the friction force in the negative direction. We divide by the mass m, and we see that the m cancels, and we get the deceleration, remember, deceleration is just a type of acceleration, but the car is slowing down, so it's a deceleration. But the acceleration here is minus mu sub k times g, okay? The minus sign, of course, indicates the accelerations in the negative direction, whereas the motion for the velocities in the forward direction, the positive direction, so that means the object is slowing down. Now, we have the fact that the change in position, x final minus x original here, is 290 meters. So we can solve out for the final speed, or the original speed of the vehicle, assuming it's at rest at the end. And we take that equation, we substitute in, we solve out for v0, and we find that the original speed of the car here is going to be 58 meters per second. 58 meters per second. So remember, 25 meters per second is 56 miles per hour. So 58 meters per second is approximately 130 miles per hour. And it was moving at least that fast because the marks actually ended only because as it says here, actually the marks ended only because the Jaguar left the road after 290 meters, so it may not have been even stopped yet. So it took at least 290 meters of skid marks, and assuming mu sub k was 0.6, 130 miles per hour at least, maybe faster. Now here's an interesting problem from your book. We're going to go through. It says a block of mass m equal to 3 kilograms slides along a floor while a force F of magnitude 12 newtons is applied to it at an upward angle theta. The coefficient of kinetic friction between the block and the floor is mu sub k equals 0.4, and we can vary the angle of the pulling force, right, the applied force, anywhere from 0 to 90 degrees, assuming the block remains in contact on the floor. So it says, what angle theta should we pull the force at to give the maximum value of the block's acceleration magnitude A? In other words, what angle should we pull with to make the block accelerate make its acceleration have as great a value as possible? So if we draw a sketch of this, basically we've got the block and we're going to apply a force here at some angle theta. We've got the in the y direction, we've got the weight of the vehicle, or the weight of the block downward towards the center of the earth. We've got our normal force upward supporting the block, but remember, because we're pulling upward at an angle, that y component of our pulling force is going to add into the positive direction here. And we're going to make the assumption, as it says, that the block remains on the floor. In other words, our force size is not going to be large enough to actually lift the block. F sub y there is not going to be large enough to actually overcome the weight of the block. But of course, that F sub y value, depending on what angle we pull at, is going to affect F sub n. So we want to try to figure out here, what angle should that be to get this block accelerating as fast a rate as possible. It's tempting to think, well, just pull it directly to the right. But is that the right answer? Because if I pull it directly to the right, then I have no lifting up force here, right? So the normal force is bigger, which means I have more friction. So the idea here is if I pull upward a little bit, right, with that additional F sub y upward, F sub n can be smaller, and if F sub n is smaller, I have less friction. So there's going to be some angle here, and rather than guessing at it, we want to basically prove to ourselves what angle that would be. So again, we start with our little sketch there of the situation. We write down the values that we were given, 3 kilograms, 12 newtons of force, and mu sub k is 0.4, and we want to find the theta angle here for maximum acceleration in the x direction. Looking in the y direction, again, there's no acceleration up or down here. The assumption is the block's going to slide directly horizontal along the surface, and so the y forces should sum to 0 because there's no acceleration in the up and down direction. So when we add up our y components of our forces, that would be what? F sub y plus F sub n minus F sub g, and that better sum up to 0. Of course, F sub y here is just going to be F times sine of that angle theta, right? So so again, if we go ahead and start writing this out, F sub n upward, F sub y upward, F sub g downward. We know that F sub y is going to be the size of the force times the sine of theta, right? So we know the size of the force here that was given. We know how big that is, but we don't know the angle, right? And so we go ahead and put those in. And then the weight of the block, we can figure that out, right? The force is gravity, or the weight is mg. And so mg here would be 3 times 9.8. So we end up with this equation. And of course, we can simplify that down to solving out for F sub n, and we get F sub n as 29.4 minus 12 sine theta. All right, so now we can turn our attention to the x direction. And we look in the x direction, we have the x component of our applied force, right, which we'll call F sub x. We have the friction force acting to the left. So those two forces are acting in the horizontal direction, and they should be equal to the mass of the object, the mass of the block, times its acceleration in the x direction. So when we go ahead and write that down, and we add up our forces here, F sub x to the right, F sub k, the friction force, to the left, that has to equal the mass of the block times the acceleration. We know that F sub x, right, the x component here of our applied force is just trying to draw this. Here it is up there. F sub x, the x component of our applied force is just 12 cosine theta, so we plug that in for that. Of course, the friction force is mu 0.4. They told us that, right? And then we multiply that times the normal force. Well, the normal force we figured out on the previous slide was 29.4 minus 12 sine theta, and then we set that equal to the mass of the block times the acceleration. Mass was 3 kilograms. So we end up with this equation. And of course, if we simplify it, by factoring through, we can multiply 0.4 times 29.4, and then 0.4 through times minus 12 sine theta. And remember, we have a minus sign there. So that's going to make this term here negative, and this term will turn positive because we have a minus times a minus, right? So anyway, doing all our math there, if you're careful with it, you end up with 12 cosine theta minus 11.76 plus 4.8 sine theta equals 3a. And if we solve this out for a, which is what we'd like to do here, we get that the answer is a is equal to 4 times cosine theta plus 1.6 times sine theta minus 3.92. Now, that's our relationship between the acceleration and the angle theta, right? However, they wanted us to figure out at what angle theta gives us our maximum value of a. So what we have here right now is a as a function of theta. So what we need to do when you want to find the maximum value of a function, do you remember what you do? You take the derivative of the function and you set it equal to 0. And that allows you to find the places where there are mins and maxes. And so that's what we're going to do here next. So there's our equation, and we want to find its maximum, right? And in calculus, to find where a function has a maximum or minimum, we take the function's first derivative and we set it equal to 0, and then we solve it. Okay, and that's going to give us the position, that where the function has either a maximum or a minimum. Now, I'm not sure where you are in your calculus studies, how far you are along in your calculus, but if we take the derivative of cosine with respect to theta, if we take the derivative of cosine, we get minus sine theta. And if we take the derivative of sine theta, we get cosine theta. So there's no negative in this one. But cosine differentiates, or we take a derivative of that, and it gives the minus sine theta. Derivative of sine theta is just cosine theta. So when we take the derivative of a with respect to theta, right, dA d theta, we would get minus 4 sine theta plus 1.6 cosine theta. And then, of course, this has no theta, so that's like a theta to the 0 power, remember? And so that whole constant term will just drop out. And so that is our derivative, our first derivative with respect to theta for a, function a. And then we set that equal to 0, right, to solve for the mins and maxes. So what we have to do is solve that equation now to find out where the min or a max is here. And, of course, when we take that and rearrange it a little bit, we can move the 1.6 cosine theta over to the right side, and we see minus 4 sine theta equals minus 1.6 cosine theta. Now, if you think back to your trigonometry, sine over cosine is tangent. So if we divide both sides by cosine and then divide both sides by negative 4, we can end up with sine theta over cosine theta equals 1.6 over 4, right? And of course that's tangent, and so the inverse tangent of tangent theta is going to give us our answer. So the theta here is going to be the inverse tangent of 0.4, and we get 21.8 degrees. Now, notice that by plugging the numbers in, like we did here, by plugging the numbers in from the beginning, we have these numbers here, and we followed through, had numbers, and we get our answer, right? So now this is the right answer for this particular situation. Right? But now, and that's good. I mean, we solved it out. There's nothing wrong with what we did. But what if now somebody were to actually change some numbers on us? What if they were to say, oh, I got the mass wrong, or we're going to do a different coefficient of friction, or whatever? The way we did the problem, we'd kind of have to trace back through our whole problem, plugging in the new values. So wouldn't it have been nicer if we had solved this problem without using any numbers, just using all variables? We would end up with a cookbook formula. And so that's what I want to show you here next, is how we would have solved this problem without numbers in it. And it's really not all that much harder. So again, not that we did anything necessarily wrong in the previous problem, but is there a way we could have done the solution to the problem better? And for example, if someone tells us, oh wait, the coefficient of frictions is actually 0.6, and the other value I told you is different than that, we'd have to trace back through our whole solution. If we get enough confidence in our algebra and we practice this enough, we can actually solve the problem and wait until the end for plugging in any numbers. And if we can do that, and that's something to challenge yourself with in your study times, to try to practice this some. Okay, solve the problems without putting numbers in until the very end. And if we had done that, notice the power of this method. So going back, our x and y equations would have looked like this. Without putting any numbers in, we would have just had f sub n equals mg minus f sine theta. right? Not knowing what the F value is and not knowing what the mass of the block is. Our X equations would have looked pretty similar. This equation right here looks pretty similar to what we had, I hope, right? It's just instead of having like numbers in for F and mg, putting the weight and the value for m in there and the value for mu in there and so forth, we just have them as variables right here. Okay, but we just proceed. We proceed the same sort of way. So instead of being able to simplify all that up and add it together and so forth, we end up, you know, as simple as we can get right there. Solving then for a, we find out that a is equal to 1 over m times f cosine theta minus mu sub k mg plus mu sub k f sine theta. And now if we divide through, we factor that m through the entire equation, through each term, we end up with this. We end up with an equation that says, hey, your acceleration is going to be f over m times cosine theta minus mu sub kg plus mu sub k f over m times sine theta. So again, a little more complicated? Yeah, a little more complicated, but keep in mind that these are just, you know, these are just numbers, you know? I mean, we're just dealing with them like they're numbers, right? Now, whoops, like that. So the only functions with theta in them is this term and this term, right? This is kind of like a constant, right? And so now we go ahead and do our math. What do? We want to find the maximum value of A, right? Where A has a maximum. We need to differentiate the function with respect to one of the variables, and the variable that's that we can fluctuate here. The other things are going to be set values depending on the situation, but the theta is the thing that we are trying to figure out what angle theta we get our maximum A value from. So again, we're going to take dA d theta and set it equal to 0. And so let's go ahead and do that. All right, so there's our equation, and we've got to differentiate it. Remember, when we take a derivative of cosine, it turns into minus sine, and when we take a derivative of sine, it turns into cosine, right? So dA d theta equals minus f over m sine theta, right? That's this term differentiated with respect to theta. This term, as we talked about, has no theta, so it goes to 0. This term here, sine, just goes to cosine. So we have mu sub k f over m times cosine of theta. So there's our derivative with respect to theta for A. And so we set that equal to 0 as shown, and we have to solve that equation out. Well, notice that it's not really a whole lot harder to solve, right? We end up on the left with minus f over m times sine theta. On the right, we end up with negative mu sub k f over m times cosine theta. If we multiply both sides by m over f is just going to become a 1. As a matter of fact, we can multiply both sides by negative m over f, and they both sides turn positive. So then we have just sine theta equals, right, I guess I showed that in the PowerPoint slide anyway. So we end up with sine theta equals mu sub k times cosine theta. Divide both sides by cosine theta, we end up with sine theta over cosine theta is mu sub k, which of course is tangent theta. And so theta is going to be the inverse tangent of what? Mu sub k. Notice that this particular problem, when we solve it out with variables, most of them end up canceling, which means they don't make any difference at all. The maximum angle, or the angle we want to pull this at to get maximum acceleration, is going to be determined by mu sub k. We take the inverse tangent of mu sub k, and that's the angle where we're going to get maximum acceleration. So none of the other values really mattered. Now, if you go back to the previous slide, remember it was inverse tangent of 0.4. So it actually turned out, you know, if you were noticing, 0.4 was the coefficient of kinetic friction that was given to us in that previous problem, right? So we actually got the right answer when we did it the previous time, but the thing is, we got the answer negative or inverse tangent of 0.4, and you know, if you know, how do we know that that 0.4 really came from mu sub k? You know what I mean? We did so much math plugging in numbers in that previous version. It would have been hard to know whether that was just a coincidence or whether that meant something. But doing it this way, by doing the variables and not plugging in the numbers till the end, we see that the equation, the little cookbook answer to this question, not only tells us an equation that we never have to solve the problem again. People could change the f value on us. They could change the you know, whatever value they want, and the only one that's really going to matter is mu, right? And we're going to have our answer there for the right right angle. So again, we have an answer here that any coefficient of friction will work for, and we see that it is the only value we need to get an answer. All the other variables in the problem are unimportant. So by solving a problem with just variables, you oftentimes you get more insight and understanding as to what's really happening. Plus, again, you never have to solve this problem again. You know, I never have to solve this problem again, right? We did it like this, and there's the answer, right? And if somebody changes it, I go right to the answer. I don't have to trace back through all that math that we did previously, plugging in new numbers. I'm right there. Okay, so hopefully that makes sense. We're out of time for today, so this much nicer method, I again encourage you to try to challenge yourself to do that once in a while. You don't have to do it all the time, but once in a while it's probably a good idea to start practicing that. Okay, so we'll stop there for this lecture, and we'll see you next time.